Good afternoon, good evening, good morning, everyone from wherever you have joined. I just wanted to clarify that we had a seminar before where I presented on my security research on SSRC security verification in Zero Trust. So hence I chose a different topic of security that we extensively do research on. Although at the end of the presentation, we'll tie up with our research on SSRC security verification, why it's important and how does both these topics merge together, okay? So, this is the outline of our talk. First, let's talk about system security. So system security, we have used antivirus software at some point of our time, or we still use these days, right? I use a Mac computer, so probably I don't use, but if you're using a Windows computer, you might have been using Norton or McAfee antivirus softwares. The problem is antivirus software is dead, as a security expert in semantics says. Why do they say that? There are two reasons. One, as we'll shortly show, there have been a plethora of existing attacks. One of the most prominent attacks is the Colonial Pipeline, gas pipeline attack that happened in the southern states of the US last year. And these type of attacks we see every day. And antivirus software are not able to keep up with that. So there's a cat and mouse game going on over the time. And this has resulted in our all systems to be much more vulnerable than they used to be. The other problem is nowadays we are all moving towards low power battery operated devices, right? Like we are using IoT edge devices. For example, we are using smartwatches. We are even using for medical purposes, we are using the smart insulin pumps, smart pacemakers, and so on. Now imagine these low power IoT devices, when they have very limited battery capacity, when you are running an antivirus software on top of that, you are actually expanding a lot of battery life. So anytime you have used antivirus software on your own PC, you might have seen that the PC goes slow, right? One prominent example is when I was a college student, I'm sure Suresh might have also faced this, and many of you have faced this. We used to have Windows Vista operating system, right? And Windows Vista, when you had Windows Vista and you would use an antivirus software on top of that, it would get really slow. Those days, the RAM sizes were not large. They were maybe 1 GB or 2 GB RAM. So that would make it really, really slow. So as a result, the antivirus software, imagine that is running on a low power battery operated device. Let's say a smart pacemaker, right? It's very difficult to run an antivirus software, full stack antivirus software on a smart pacemaker without harming the battery life. On the other hand, if you don't use antivirus software, that smart pacemaker is prone to risk. And by prone to risk, I mean, this is a life risk. Somebody can tamper with that and lead to the death of the patient who is using the smart pacemaker, right? How do we handle that scenario? We're going to find a solution to that today. The second thing that we'll talk about is hardware security. So hardware, as we know, are no longer developed in a centralized fashion. There's a distributed fashion of hardware development, right? We have the different steps, and these are produced by a lot of third-party companies like third-party EDA vendors, third-party IPs, third-party fabrication plants, third-party packaging, and so on. This has resulted in a lot of hardware security challenges, like, for example, we see here IC counterfeiting, overproduction, reverse engineering, and hardware Trojans. We'll briefly go over these towards the end of the presentation. So let's talk about system security first, okay? So malware, or which is a short form of malicious software, has been going on for quite a long time. So malware, there are various kinds of malware. We popularly know malware as virus, but viruses are a subclass of malware. There are other classes of malware like ransomware, adware, botnets, rootkits, worms, and so on, right? And they can be used for various reasons. They can be used for stealing money, stealing confidential information, subverting critical or mission-critical applications, including military applications which might subvert a country's national security, as well as there's something called botnet, which is actually very, very dangerous. So that's what it does is, it can actually use your own system as a host to multiply itself and spread it to other systems. So as you can see from the newspaper cuttings that I have shown here, these type of malware attacks have been growing exponentially over the last few years. We'll see some of the specific malware attacks that I think are very important, that have been really, really big, that have been manifested as a big problem over the past few years. So one of the attacks that I wanted to mention first is in a fellow academic institution, University of Utah. they had to pay almost $500,000 in ransomware attack on a computer. Basically, there was a ransomware attack which threatened to disclose all the confidential student information unless that money is paid. Then we have this colonial pipeline attack. We all know this, that there was this huge pipeline of gas or petrol that was there in the southern parts of the US, and that was attacked, and as a result, the petrol prices increased a lot in last year in the US. In 2019, a large Florida school district was hit by a ransomware attack where the hackers demanded $40 million. The same thing. They said that unless you release the confidential data, unless you pay the money, they will release the confidential data. We all know the Stuxnet worm that has happened, that has attacked the Iran's nuclear facilities, and this was caused by an attack. So Tesla, one of the popular cars that these days people aspire to buy a Tesla, which is an electric car, this could be actually hacked. And there was a very cool experiment by researchers from Belgium who hacked the Tesla car with a Raspberry Pi. A Raspberry Pi costs like around $50, $60, and the other equipments that they used to hack would cost a total of like $100 to $200. And they would use that to hack a car, a Tesla car, which costs around $40,000 to $50,000. And they could easily hack that car using that tool. And they could hack the car like 50 meters away from the car. So you can clearly understand that this is a grave matter of concern. We'll talk more about automotive hacking in a few slides. Acer, one of a popular computer manufacturing company, was also targeted with $50 million ransomware attack. 22 Texas towns were hit in ransomware attack in the new front of cyber assault in 2019. So what this means is that, like, there were these Texas towns, so each town has a town government, right? Where you have the tax information and all the confidential information like date of birth and social security number. And these were attacked using this new front using ransomware. Ransomware, as the name suggests, it basically means that you attack somebody's computer and you ask the person to give you money, otherwise that you will leak some confidential information. That's basically ransomware. So the number of malware signatures have been growing exponentially over the past decade, as you can clearly see. And this is not only restricted to PCs. Over the past decade, mobile phones, Android applications have increased enormously, and the number of Android malware signatures have also been growing exponentially. There are 4 million new Android malware samples every year. So what is the reason why existing antivirus solutions are ineffective against modern malware, right? Let's first try to investigate that. So modern malware are mostly of two types, polymorphic and metamorphic. As the name suggests, morphic is a keyword, which means that they modify itself, right, or change itself. So polymorphic malware modifies itself to avoid detection. They use a mutation engine, and the structure of the malware changes and not the behavior. Metamorphic malware, on the other hand, rewrites itself in each iteration of propagation. So each version of the source code is different from the previous version. Now notice here one important thing, that this malware, the structure changes and not the behavior. This is very important. Let me explain how this works and why this is imperative in understanding why existing antivirus software cannot detect this. So what does this mean? Let's consider an example of a GPS malware, right? The GPS malware will log into the GPS device. It will hide itself. It will log the GPS data and it will transmit it outside, right? It will do these functionalities irrespective of how the malware has been structured, right? It doesn't matter how you write the malware, how you compile the malware to generate the executable, the behavior will remain the same. It's exactly, or not exactly similar, kind of similar like this COVID virus that we are seeing, right? It changes itself. We have different variants always, right? So although the variants change, that means the structure changes, so the existing medicines are unable to detect it, or existing attacks are unable to prevent, existing defenses are unable to prevent it. However, the functionality of this COVID malware remains the same, right? They will change your temperature, infect your lungs, and so on. So same thing happens here. So the behavior of the malware changes, not the structure. So that's what the example I was giving you. The behavior of the GPS malware doesn't change, but the structure doesn't. But the structure can change. Okay, the behavior remains intact. Now, why is traditional malware detection ineffective in this case? Because traditional malware detection is exclusively signature-based. The malware that we use in our PCs in regular days, these are signature-based. So what does signature-based malware means? store a software signature and then validate the software signature using a set of known signatures. So let's see what it means. We have a repository of known software signatures, right? So when we run a new program, like for example, we are running Microsoft PowerPoint here, and all of us are running Zoom in our systems to attend this seminar. So Zoom is a software, right? So when Zoom is being run, the antivirus software will create a signature from the Zoom executable and will constantly keep on mapping it to a set of known malware signatures. If there's a map, it will raise a flag and will say that there's a malware detection, a malware attack. If there's not a map, it will say that this is not a problem, okay? The problem with this is it can be easily subverted because at the end of the day, it's a software. The other problem is it's ineffective for morphic malware. So it's imagine you have the picture of Spider-Man and Peter Parker, right? We know that they are one and the same guy. So these two people, but the face changes. So if you cannot identify, but they have the same characteristics. Both of them, like Peter Parker, even without the Spider-Man suit, he can operate exactly like Spider-Man, right? He can throw the spider webs and he can jump off buildings and so on. So, but however, if you cannot identify them, that's like the signature-based malware because the signature is being created from the picture of the person, right? Not from the behavior of the person. So how do we circumvent this? The other solution is to develop a behavior-based malware detector. So it extracts the software behavior. As we were mentioning the GPS behavior, it will extract the GPS behavior, right? However, then why it is not used, it's very good. Then it can detect morphic malware. The problem is it has very high overhead. So it is not actually practical for PCs and IoT devices, okay? So that's the problem of behavior with malware detectors, okay? So now, then the researchers try to find out what are the solutions for that. How do we find out, how do we develop new or efficient malware detection schemes that can actually help circumvent the problems of signature and behavior-based malware detector. So the first thing people came up with something is called hardware-based malware detector. So the whole idea is use the hardware as the root of trust. A hardware is much more difficult to undermine compared to a software. See, if you want to undermine a software, you can always go and escalate your own malware privilege, de-escalate the antivirus privilege, antivirus software privilege, and therefore subvert the antivirus software. But if you have to do the same thing on the hardware, you have to go and physically tamper with the hardware, right? Which is extremely difficult to do. So therefore, these hardware-based malware detectors actually use the hardware as a root of trust. So the first thing that people used are hardware performance counters. Hardware performance counters are dedicated registers found in almost all modern processors, which are used to detect some microarchitectural or architectural events like number of branch encountered, number of branch misses, number of cache misses, and so on, right? These are typically have been developed for a long time, for almost like 20 years. Or more than that. They're used for improving compiler or system performance, right? And since they're already present in the system, incorporating them for malware detector doesn't introduce any hardware override because they're already present in the system, right? So why does HPCs or hardware performance counters work in malware detection? So if you see the graph here, we have plotted for different SPEC benchmarks. These are common architectural benchmarking programs. We have plotted various hardware performance counters like L1 exclusive hits and the number of arithmetic microoperations executed. So as you can see that each benchmark program has a distinct variation with time of the HPCs, right? So if you can create a signature based on these and store it on your system, you can easily discriminate between these programs. Now, do a thought experiment based on this. If you can create a signature based on a set of known malware data and a set of known benign data, and you can do this classification, you can easily identify which is a malware and which is a benign program. Okay, so in this way you can detect a malware using these HPC signatures. Now you can ask that what's the difference with existing signature-based antivirus software? That's also a signature. Agree. The difference is these signatures are created using bit strings, and the signatures that are used in antivirus software are created using executables. So those are software signatures which can be subverted. These are hardware signatures which will never be subverted so easily. Okay. So, and using these hardware-based malware detectors, this is no longer a thing of like a science fiction story. This is real. Intel is actually collaborating with Microsoft to develop Intel's threat detection technology, which is Intel's TDT. What they're doing is they're using Intel's TDT to improve Microsoft Defender endpoint protection. Specifically, they're trying to detect crypto miners using these hardware-based malware detectors. Okay. So what did we do here? So first, we developed a theoretical model for hardware-based malware detectors, and we can see that the probability of malware detection increases with increase in number of hardware performance counted events and the reduction in the sampling interval. So a processor has a lot of hardware performance counters. A normal Intel processor has like hundreds of hardware performance counters. A Raspberry Pi has 20 hardware performance counters, but you cannot monitor all of them simultaneously at the same time. You can monitor only 4 to 6 of them at the same time. So the probability of detecting a malware increases with the increase of HPC events and reduction in sampling interval. That is how fast you can detect these malwares, like how frequently are you sampling them. Of course, the best idea is to sampling them every cycle, but that introduces a huge overhead and you wouldn't want to do that. So HPC-based malware detection. So this we are using the machine learning classifier. So we will use these HPC data. We collect from a set of benign programs, a set of malware programs, and we use a machine learning classifier. So this is how it works. So you collect the HPC data, you train a machine learning classifier from a set of known and benign malware programs, and then when an unknown program comes, depending on this classifier, it will predict a classification whether it's a benign or malware. So these HMDs efficiently detect malware activities, and the question is which machine learning classifiers are best. To answer this question, we'll first look at how HPCs are collected. So the collection of HPCs vary based on the processor architecture. Linux actually uses a command called perf, which is used to measure HPCs. So the perfstat command returns the value of HPCs. For example, this is an example of perfstat command where you have perfstat, and the one you can see here means it's collected 1 millisecond, the frequency. The HPC we are measuring is the branch instructions, and of course, a.out is the executable. You can use the zoom executable also to collect the HPC for the zoom program, and you can see how the HPCs vary. That's actually pretty cool. So the experimental setup to measure in our experiments that we will do is we use the Raspberry Pi 3 model, because the reason we don't use a PC is when you run this malware, if you use your PC, they can damage your PC, right? In a Raspberry Pi, you can always flash your memory using the memory card, and as a result, there's not a big problem with infecting the Raspberry Pi. But you cannot flash the OS of your PC so often. So we collected 300 benign malware programs. The benign programs were sorting and computational algorithms. And we use this website VirusShare to obtain processor-specific malware. VirusShare, if you do not know, is a very cool website which hosts a lot of viruses. So you have to create a login, and then you can actually download real-life malware and use it, okay? And they give you processor-specific malware. Like, for example, if you want to run on an x86 system, they will give you that. If you want to run on an ARM system like a Raspberry Pi, they will give you ARM malware. And so we used various classifiers, and we used the parameters of this classifier, which is best. So this is the overall framework, as you can see. And we use 7 classifiers, which are decision tree, nice bias, k-nearest neighbor, linear regression, random forest, support vector machines, and neural networks. Now, one thing you might ask, for those of you who are into machine learning, you can ask is, why didn't we use some complex machine learning classifiers like CNN and all those things, right? The reason is that if you remember, the fundamental motivation is to use this in a low power system. So the point you use something like CNN, a complex machine learning framework, that increases the overhead, right? Running a CNN takes substantially way more amount of energy compared to a decision tree or a random forest, right? So that's why we try to keep the classifiers simple. So we saw that the random forest performs the best among all, and utilizing inferior parameters can produce performance which is suboptimal. So then we looked at adversarial attacks on HMDs. Now, adversaries can produce an attack that obfuscates the HPC traces. The adversarial attack consists of 3 steps. So basically what you do is you reverse engineer the hardware-based malware detector using a black box technique. Then you use adversarial sample predictor. So basically you use a sample predictor to predict the adversarial sample. and they use an adversarial sample generator. So what happens is there's a malware and a benign program that is run on the same thread. So as a result, what happens, the HPC values of the malware changes because of the benign program, right? And due to that, the machine learning classifier now gets confused as to which is the malware and which is the benign program, and it produces incorrect output. So to counter this, we produce what is called a moving target defense. So what we did is we used a lot of classifiers, and we randomly select one of the classifiers from this bunch of classifiers to detect which to use one of these in detecting these attacks. The advantage is the reverse engineer will not be able to reverse engineer which classifier we're using. We actually developed a mathematical computation which we showed that detecting this which classifier is useful is actually very low. It's a probability of 10 raised to minus 1,000. So what we can definitely do, how we select these various classifiers. So we select these various classifiers by the theory that, remember I said in a processor there are like hundreds of HPCs, but at the time only 4 to 6 can be monitored simultaneously. So so you can select which 4 to 6 you can use, and then you can randomly choose one of the classifiers, right? So you can build a lot of classifiers and then randomly vary that, and that will actually help you to detect which class. That will actually help you to prevent or defend against these adversarial attacks. And let's look at the results. So if you see the results, the initial recall was 74 to 72%, but it reduced to 50 or almost 50% after the attack. Now 50% recall means almost a random guess. So the machine learning classifier is not doing anything, right? So we could actually improve the recall to 70 to 77% actually after the MTD, after the moving target defense for these two classifiers. Now, I was talking about automobile security, right? Let's see some of the news articles. In 2015, Chrysler had to call back 1.4 million Jeep vehicles because of a Jeep Cherokee attack. This is very interesting. So 2 researchers in St. Louis, Missouri, they did this experiment. So one of them were driving on the St. Louis highway. The other person was sitting inside an office. And the person driving on the highway suddenly realized that he doesn't have control over his brakes and accelerator. So imagine you are driving on a highway wherever you are in the world, and suddenly you're driving at say 70 miles an hour, and suddenly you see that you don't have controls over your brake and accelerator. What would you be doing? You would be like really nervous, right? And you can potentially die. So actually Chrysler had to call back these vehicles to fix this. And on the right side, if you see the screenshot, that's actually McAfee developed an attack on automobiles, and they showed that this kind of attack can be done. This is a ransomware attack. So basically, you can block your system and on a car, and unless you pay money, your car will not be unlocked. So how do attackers attack the automobiles? They attack through automobile ECUs. So the vehicles have a plethora of potential attack vectors. You have the electronic control unit, the infotainment system, the airbag control unit, the telematics unit, etc. Right? So what happens is the compromising the control units can engender devastating outcomes. So the ECU is the most vulnerable. So these systems are all connected to the internet, and once you hack into these systems, you can actually hack into the car. And attackers could triple brakes or eavesdrop on the victim. So we developed a very cool experiment. We did a crankshaft modification attack, right, to halt the engine. So basically, there's a crankshaft sensor, which we sent an erroneous signal to it for 1 second. So it ideally expects a value in the range of 1 to 24. We gave it a value in the range of 0 or so on, right? So what happens is the piston valve open and closing for air, it stops. So long story short, what happens is the brakes are applied slowly. So imagine you're driving fast and you see suddenly an obstacle on the road and you want to press your brakes fast. This will prevent it. This attack will prevent the brakes from doing so. So the brakes will be applied slowly, and as a result, you can potentially hit the obstacle. So we used HPC-based system to detect the attacks. We did this experiment on a Mitsubishi car, and we used different machine learning frameworks, and we saw we compared various machine learning frameworks, and we saw autoencoders perform the best. Now enough about security. Let's talk something about privacy, right? So user privacy is very imperative for mobile applications, and the number of children owning their smart devices is increasing exponentially. Like you can see in 2011, while number of children owning their tablets in the US was less than 1%, in 2018 it has risen to more than 40%, right? And if we have some child in our home, we see children these days use tablets and cell phones, not only for games, but also for a lot of entertainment and infotainment system, like learning colors, learning numbers, learning animals. People are more prone to using game tablets or cell phones for that. This has resulted in an increase in the number of internet crimes against children. In 2017, the FBI reported 1,300 crimes against children. Okay. So data breach exposed for Kids, which is an infotainment website that exposed information of 1,700 children. So what does the Federal Trade Commission or the FTC do? The FTC takes a lot of actions. So for example, FTC warns children's app maker Baby Bus against COPA virus, and we'll talk about COPA. There's a $5 billion penalty that was put on Facebook recently. InMobi had to pay $1 million. And TikTok was fined $5.7 million for violating children's privacy. So actually, the FTC developed a rule called COPA, which is Children's Online Privacy Protection Act. What does this mean? This means that if you are developing an app for children 8 to 13, you cannot leak some sensitive information. Let's look at an example. For example, we all use radio cab services like Uber, and we have in US something called Lyft. I'm not sure what you have in the UAE, but in India, we have an app called Ola, which is similar to Uber, where you can call your cab, right? For that app, you typically transmit your location services, right? Because without the location services, the cabs won't know where you are there. However, for children's apps, like an app which is designed for teaching children different colors, that app doesn't need to transmit the location, right? It has no business of transmitting the location. However, that's not clearly abided by a lot of apps. So to prevent these, there's this act called COPA, which prevents these apps from transmitting. However, unfortunately, there is no standardized way for guardians to know whether an app they're using for their children is COPA compliant or not. And moreover, these apps update themselves very sporadically. So maybe an app will update themselves while you are in sleep. And it was COPA compliant yesterday, and today it becomes non-COPA compliant. How do you dynamically verify that? There has not been a solution to do that. So we actually proposed the first HPC-based solution to do that. And we developed this app, we developed the system where it can detect whether an app is COPA compliant or not. This paper received significant media coverage in NBC Austin, CBS Dallas Fort Worth, UTD News, and Science Days. Now, what are the disadvantages? We looked at so good things about using HPCs for antivirus software. What are the disadvantages? Now, HPC has several disadvantages. One is non-determinism. The same program running on the same system can have 5% difference in HPC readings. It introduces high false positive rate, which is very problematic, right? Imagine you're running Zoom and suddenly your antivirus system claims it as a malware. You don't want that. The HPC readings inside a virtual memory machine differ from that of an actual hardware. These are not real time. The system needs to stop to collect HPC data. So how should we circumvent this? So to circumvent this, we propose something called trace buffer-based malware detection. So trace buffer-based malware detection has all the advantages of hardware-based malware detection, but doesn't have the disadvantages for HPC. So let's see how we work on that. First, let's take a step back and understand what trace buffer is. This is a very simplistic picture of a chip design. You have the implementation at the gate and RTL level where you have the pre-silicon verification. Then you have the manufacturing where each copy of the integrated circuit is where you, after that, you use two steps. One is manufacturing testing, one is post-silicon validation. Manufacturing testing is used to ensure that the chips do not have electrical defects, right? And therefore, it's done on each copy of the IC. Post-silicon validation, on the other hand, is used to verify whether there are no functional violations that have escaped from the pre-silicon verification phase and have manifested themselves in the manufactured chip, okay? So the post-silicon validation is done on only one copy because the functional bugs that have escaped the pre-silicon verification, that will be present in all the copies of the same chip. So the design validation complexity have been growing exponentially over the years. We all know this. And post-silicon validation as a percentage of total design resources have also been growing exponentially. Now, the problem of post-silicon validation is limited observability. Imagine you are debugging a code, a software code, say a Python or a C code, right? What do you do? When the code is not working well, you run it on a debugger, right? You run it on a debugger, and then you introduce breakpoints and observe the internal variable values. Now, the problem is when you are debugging a chip and the chip is already manufactured, you cannot put in breakpoints, right? Because the chip is already fabricated. You cannot break open the chip and observe the internal values. So how should we circumvent this? To address this problem, the researchers came up with something called trace memory or trace buffer. So the trace buffer stores some internal signal states which act like a breakpoint. So basically, these trace signals are designed during the design phase. So these trace data will be obtained through a JTAG interface, and you can observe some of the internal signal states. Now, of course, since the trace data doesn't contribute anything to the functionality of the chip, the trace memory has to be as low as possible, right? So it's less than 2% of the signals are stored in the trace memory. You cannot store all the signals in the trace memory. So the question is which signals to choose. To answer that question, first let's look at how it works. So this is again a more detailed picture of how post-silicon validation works. So you have the test inputs, which goes to the logic. And from the logic, the trace signals go to a trace buffer, and then they go to an offline debugger for debugging. So the trace signals have two parts, width and depth. Width means the number of trace signals which are stored every cycle. In this case, the width is 32. And depth is the number of cycles over which the trace signals are stored. In this case, it is 1024. So after this 1024 cycles, the trace memory is rewritten. It's like a circular buffer. Okay. So trace signals are actually designed using some logic called signal restoration. So what does signal restoration mean? Signal restoration means that you try to restore the untraced signal state. So you trace some signal and you try to restore the untraced signal states. For example, in the top picture, you can see a 2-input AND gate, right? Now this 2-input AND gate, this 2-input AND gate has two inputs A and B and the output C. Now if you trace A and if you see the state of A is 0, you know for sure that the state of C is also 0, right? That's a forward restoration. Backward restoration, on the other hand, means if you're tracing an output and trying to restore the input. So in the first picture here on the bottom, you can see that you are tracing C and the state of C is 1, and the state of C is 1. You know for sure the states of A and B are also 1. In the second picture here, you are tracing C. You know the state of C is 0. You trace A, you know the state of A is 1. You know for sure the state of B is 0, right? So in this way, you can use backward restoration to trace an output and one or more inputs and trace and restore the output. In the last picture, as you can see here, the state of C is 0. The state of A is also 0. So you know for sure that the state of B, you cannot know, right? Because the B can be 0 or 1. So in this case, backward restoration actually fails. So this whole state restoration logic is used to trace the signals. You store the signals which give the highest restoration. Let's see this example where you have a system of 5 flip-flops. So you are tracing C, and you're trying to restore A, B, D, and D. So in the table here, you can see that C is being traced every cycle, right? So C has a value of 0, 1, 1, 0. And the others have a value of 0, 1, or X. X means that they cannot be restored. So let's take an example. Suppose state of C in cycle 0, you can restore state of D in cycle 1 as 1, right? By forward restoration. Similarly, knowing state of C in cycle 1, you can restore state of A and B in cycle 0 by backward restoration. And now that you know B and C in cycle 0, you can restore state of E in cycle 1 using forward restoration. So in this way, you can actually restore a lot of states using restoration algorithms, okay? So let's get back to a story of malware detection. Now that we have a comprehensive idea of what a trace buffer is and how the trace buffer is designed, let's see how this can be used for malware detection. So trace buffers can be easily accessed by JTAG interface, and trace buffers store hardware footprints for different software being executed for both benign and malware software. So when you run a program, so what happens is when you run a program, that program creates some hardware footprints on a trace buffer. And using these hardware footprints, you can classify whether a program is benign or malicious. So the trace, similar to the HPC signatures, you are creating a trace signature, trace buffer signature, right? It has all the advantages of benefits of hardware-based malware detection. Do not incur any performance penalty on other applications. It supports low latency malware detection, as we'll shortly see. And it has lower false positive compared to HPC-based detection techniques. So as you can see here, we used an OpenSpark platform, which is an open Python by Princeton University. The experiments were ran on actual hardware, not a virtual machine. And we used IoT botnet malware from VirusTotal website. We used two different kinds of malware, which are GasGuide or Bashlight and Mirai. And we used our trace signal selection tool called SIGSAT. And we used 4 machine learning classifiers. And in the results, you can see that we can actually detect in very low cycles. So the highest number of cycles we need is 528 cycles, which if you use a processor of 1.6 gigahertz, which is less than a microsecond, right? This is 3 magnitude faster than existing software-based antivirus solutions. We have a very high true positive rate and very low false positive rate. We use cross-family validation, so you train on one family of malware and validate on another family of malware, and we can actually detect them with very high confidence. And then we used different trace buffer width. So as you can see here, increasing the trace buffer width increases the true positive rate, which is quite obvious, because with more trace buffer width, you get a deeper insight into the chip, and that helps you to understand whether the program is malicious or better. Similarly, it reduces the false positive rate, because again, more trace buffer width means more insights. So to summarize, the debug hardware efficient in malware detection, low latency, low hardware overhead, and machine learning is useful to classify benign and malicious software signatures. The challenges are which signals to choose for malware detection. Right now, we are repurposing the signals for post-silicon validation, but are they useful? Should we choose some other signals? Should we use different set of signals for various malware types, and how to improve the machine learning classifier latency? Now we'll go on to the second part of the talk, or the last part of the talk, which is hardware security, right? So till now, we were thinking of hardware as the root of trust, but is that a valid assumption? Let's see. So before globalization in the 80s, IBM used to make everything in-house, right? They had their own design, their own EDA tools, their own fab, and everything used to be made in-house. However, with globalization, it's in a distributed development environment, right? And as a result, this can result in a lot of security vulnerabilities that can creep in. Okay, so one of the security vulnerabilities that we are really concerned is hardware Trojans. These are malicious changes to a design intentionally inserted by an attacker. So you can think of this like a time bomb. Like for example, you say Apple is using a distributed manufacturing environment, right? So in this distributed manufacturing environment, if there's a third-party player, any third-party player, who introduces a small counter in the iPhone chip, which will count till 1 year, and then it will stop the chip. It will just completely stop the chip. So say you buy the iPhone today is March 28th, 2022, you buy the iPhone today, and then on March 28th, 2023, the iPhone suddenly shuts down. It doesn't work, doesn't boot. So you will blame Apple for that, right? Because as a consumer, you think it's Apple's fault that they have given you a buggy system. But it's not Apple's fault. It's the fault of the third-party player who has introduced that counter-based design to do this, right? So this is called a hardware Trojans. And hardware Trojans can be used for various purposes. Not only for doing this thing called denial of service, which is subverting a design, you can use it for other purposes, like for example, leaking confidential information. Imagine if this chip is being used in any military purpose, leaking confidential information can have disastrous circumstances, including the subversion of national security, okay? Now, Trojans are, of course, inserted with the intention of being stealthy. If the Trojan is very apparent, it will be detected easily, and you can easily identify this Trojan. Imagine, like, think of this, what I tell in the class is, think of this as a terrorist activity. A terrorist, when he or she wants to hide a bomb, the person will not hide a bomb in an open area, right? He or she will try to hide the bomb in a very confidential place, so that that's not easily detectable. Now, Trojan has two components, trigger and payload. So trigger means the thing that will activate the Trojan. Remember the example that I told about the iPhone Trojan? The trigger is the counter that is activating the Trojan. That's counting till 1. Payload is the effect of the Trojan, which is shutting down the chip, right? Now, there are various Trojan detection methodologies which are functional and side channel based. However, till date, none of them are foolproof for detecting all kinds of Trojans. So what we are doing here, and how does this come up with our collaboration with TII, is we're trying to develop an SOC validation methodology to detect vulnerabilities. So basically, a Trojan can be inserted if your chip has some vulnerabilities which can be exploited to introduce a Trojan, right? So if you can stop the vulnerabilities, then the Trojan insertion stops. So instead of Trojan detection, we are stopping Trojan insertion by closing in all the vulnerabilities, right? If your chip is foolproof, security proof, then there can be no way somebody can introduce vulnerabilities because you will be closing down all the security angles. That's what we are trying to do, and we are in the process of doing it with TII. So the other security issues which we'll quickly mention are counterfeiting, which I said, imitation of critical ICs. So this is a very interesting thing. If any of you had attended DAC 2019, there was a VP from Cisco who actually showed that counterfeit ICs are more real than real Cisco ICs, okay? The other problem is reverse engineering, which is piracy of intellectual properties by copying somebody's IP. Overproduction. So, for example, you use a third-party foundry. A lot of companies are fabless these days. So, if you use a third-party foundry and you ask the foundry to make you 1,000 copies of a chip, the foundry makes 2,000 copies. It gives you back 1,000, and it uses the rest of the 1,000 for its own benefit, right? How do we prevent against that? We propose something called watermarking, IP watermarking, which can be used to protect design integrity and copyright. It can be used during legal proceedings as well. So to conclude, malwares are a real threat in today's world. Hardware can be used as a root of trust. Debug hardware, as we have shown, are actually useful for malware detection. The distributed manufacturing environment introduces security threats in hardware. We are developing software SOC security verification, which is imperative to secure future IoT hardware.